Okay, so thank you for joining for the seminar. So we are pleased today to get to have a short visit, a week, 10 days visit from Kartik Sheth, who is, as you probably know, it has been a long process, but Kartik is...
it hasn't finished yet.
It hasn't finished yet. So we joined the lab for 3 years, starting around June this year. So he got selected for the Safe Place for Science. You remember we have the event in June. And he also was selected for Choose France for Science. So he got the two grants. So which is a great opportunity for us to have Kartik working with us during this 3 year period. So Kartik Sheth is a former associate chief scientist at NASA. So he was dealing with all the space mission, I guess, for Roman. You've probably been involved in the process of Roman selection. And he was also working at the White House for the science also, and DOE. We knew Kartik since a long time because he has been working in the COSMOS collaboration. We started in
2003.
2003. And COSMOS is one of the big projects in the house as well. So we know him very well. And that will be a great pleasure to have him for 3 years here. And he will tell you more about his path around science and politics. And so please, Kartik,
thank you.
Let you describe it.
Okay, thank you. Thank you very much. Can you hear me if I stand here? Okay, excellent. Well, thank you. It's such a pleasure to be in Marseille. This is the longest I've stayed in Marseille, and I was telling my wife yesterday or the day before, I said, I'm falling in love with Marseille because it's a beautiful city. Yesterday I got to walk all around Notre Dame, and it's just lovely. My French is terrible. I'm on day 120 of Duolingo, so if you want to help me practice my French, I would welcome it. But it's very elementary right now. I divided the talk into 2 parts. One is really talking about the core of the science that I have done and plan to do here in Marseille. But also the second half is really about my journey through my scientific career with the idea that if something in there interests you, or it's something that you want to do in addition to the science you're doing here, or the engineering you're doing here, or the research you're doing here, then let's talk about it and think about ways in which we can partner. So colloquia, it's good that it's in the morning, but a typical colloquium looks like this, where the understanding of the audience goes down after 20 minutes to 0%. If you're listening to a politician, your understanding is all over the place. But this is my goal, is I hope we don't dip below 50%. So if we do, please just raise your hand and stop me, and I would really appreciate that. Most of the work I'll describe today is with this very large international team, which includes the COSMOS team, S⁴G, which I was the PI for, and some work that we started to do with Magellanics, although I won't have time to describe that. The different colors simply indicate people with permanent positions, people who are postdocs, people who are graduate students, and people who are undergraduates. And then they work with me. It took me a while to talk about this, but let me go on to this slide. This slide captures what all of us, whether you're a biologist, a chemist, a physicist, an astrophysicist, are involved in doing. We're trying to piece together this jigsaw puzzle of our existence, of our origins. And I'm very interested in really understanding the formation and evolution of galaxies, and in particular, disk galaxies. If we look around our local universe, we can divide the local galaxies in our neighborhood into elliptical galaxies and disk galaxies. And then furthermore, disk galaxies are split into normal spiral galaxies and barred spiral galaxies, and we have a lot of irregulars. Of course, the best-selling book in 1929, I think, was one of the best-selling books. It was Hubble's classification schemes, and that was a huge advance in our field because it allowed us to understand how we can try to understand the galaxies. When you all took galaxy astronomy, you probably were told that this Hubble sequence does not represent an evolutionary sequence in any way, that SCs do not become SPs, do not become SAs. And that's true. But one of the things we also say is that the left side of the spiral galaxies here, we call them early types. And the right side we call late types. And as I'll show you, or try to convince you, that in fact that's what is actually the case based on the work that we've done. Now, even though when we talk about disk galaxies, you think about, most people think about spiral galaxies. The most common type of disk galaxy in the nearby universe is a barred spiral galaxy, like our own Milky Way. And this is M83, NGC 1365, NGC 3351. And we've known for almost 60 years that 2/3 of all disk galaxies in the nearby universe have a bar in them. De Vacloris in the RC3 catalog famously classifies them as 1/3 SABs and 1/3 SBs, with SBs being strongly barred spiral galaxies. But why do we care, right? So the important thing is these bars are like toothpaste boxes that are squeezed down. So it's a thin triaxial structure. It's an overdensity of stars in the center, and that creates torque in the gas that forces the gas off of its circular orbits into orbits that become intersecting. And you see most barred spiral galaxies are characterized by these strong dust lanes on the leading side of the bar. And that allows gas to flow down to the center. The stars don't care. They just go through. But the gas can flow into the center. And some work that we did in my thesis work showed that barred spiral galaxies are very good at rearranging the molecular gas. And I say molecular gas because bars are typically in the centers of galaxies, which is where molecular gas is more common. So barred spiral galaxies are very good at concentrating the gas into the center. Other work by Louis Ho, Zercik and Pasteroza, Phil Puxley, and others showed that barred spiral galaxies also form a lot of stars in their centers. So there's a good combination of these two effects happening. In addition to that, we know that rings and lenses are common. We don't fully understand why they happen, although we have some idea. And then we know that early and late type bars have distinct properties. So that's what we know about barred galaxies today. And we know that they're very common. But the question you might ask is, why are they so common? The answer to this comes from way back in 1970s, when there was a 10,000 particle simulation done by Hole, which you see on the right side. And in just a few dynamical timescales, this disk of stars collapses and forms a bar-like structure. Kalnas calls it a very troublesome mode because it indicates that disks are not very stable. And a very important paper, 1973, Oestreicher and Peebles concluded that bars are inevitable as soon as galaxies achieve certain conditions. As soon as a galaxy disk is isolated, cold, sufficiently massive, and rotationally supported so that it looks like a disk, it should buckle and form a bar. And that becomes the most important criteria in the work I'm going to show you. But at the time, in 1970s, dark matter was still being discovered or postulated. And the absence of bars in galaxies was used as an argument for dark matter, because it said that dark matter must be stabilizing galaxies against the formation of bars. Subsequent work, predominantly by Ilya, who used to be here, is not here today, right? Maybe she's online. So Leah did a lot of work on this, showing that even in galaxies that were initially dominated by dark matter, the bars do ultimately form. And in fact, galaxies that are dark matter dominated form stronger, meaner bars, because the dark matter provides an additional sink of angular momentum and energy. So the bottom line is, bars are a natural endpoint of galaxy evolution as soon as certain conditions in the galaxy disk are met. And so bars can be a signpost for us to try to understand when the galaxy has sufficiently matured. So if I can go back in time and try to understand when bars came into existence, I can understand when galaxies achieved the criteria to become cold, massive, and rotationally supported. Is that clear? Like, this is an important part, so I want to pause and make sure folks understand that. Okay. Just quickly showing you the work by Leah that she did. You can see this is a baryon-dominated system. dark matter-dominated system, and this one has the dark matter is rigid, and the dark matter halo is, non-rigid and rigid. The mistake that Oestreicher and Peebles made was they assumed that the dark matter did not exchange angular momentum and energy. But when it does that, you can see that the bar that forms in this system versus a completely baryonic-dominated system is very different. But the other important part also to remember is that the bar that forms, which is shown at the top in the dark line, also forms later. So what dark matter domination does is it slows down the formation of the bar. It does stabilize the disk, but when the bar does form, it is stronger and meaner and leaner. OK, so we use this idea that bars are a signpost of galaxy evolution to try to understand how the universe evolved for disk galaxies as we look back in time. And to do that, we want to use many of these deep fields, like the Hubble deep field or the ultra deep field, to try to understand this point and look back in time to see when bars came into existence. Remember, today, 2/3 of all disk galaxies have a bar. And we want to ask the question, what happened when we go back in time with bars? So there was a lot of controversy in this field for almost a decade. Using the Hubble deep field, the first set of papers by Vandenberg and Abraham showed that there was a dramatic paucity, there was a lack of bars beyond a redshift of 0.5. And if that was true, it meant it put some stringent criteria on the state of galaxy disks beyond a redshift of 0.5. We did a study with Nick Moss, so these are a couple of these are figures from that 2003 paper, where we showed that as you go back in redshift, because bars are stellar structures, you want to observe in the rest frame optical. And when you're observing in the rest frame optical, as you go further and further back in time, you need to look in the infrared today. But the problem with Nick Moss is that it cannot see the small bars because the resolution is not very good for Hubble, which is a 2.5-meter mirror. And what we concluded in this paper is that the large bar fraction was the same today in high redshift. And then there were some other studies that said the opposite. They said, oh, the bar fraction does not change. But the problem with these samples was they were very small and did not do a good job with sample selection, and there were completeness issues. So it was very clear in the mid-2000s that we needed a larger data set and better data. And so this is where COSMOS becomes very important. I'm sure you've seen hundreds of COSMOS talks at LAM, and so you've seen this figure. This is the Hubble Ultra Deep Field, Hubble Deep Field, GOODS and the GEMS, and this is the COSMOS field. So immediately you can see that this most ambitious survey ever is going to give us the data that we need because it has over 2 million galaxies over the last 10 billion years, right? So that's why this is the foundational data set for most studies of galaxy structure, large-scale structure and galaxy evolution. I'm going to show you a little video here to give you a feel for the dynamic range when you're doing galaxy morphology and trying to look for bars. Okay, so hopefully this video will play. Play, damn it. Yeah. Let me go back. See if I can get this to play. OK, let's try this. Ah. It played when I just, all right, never mind. I will, that's such a bummer. I think I can do it this way. You guys can still see this, right? Oh, it didn't work. Ah, bummer. OK, well. All right, that's too bad. I practiced this, so it's kind of weird that it didn't. OK, sorry about that. It was a beautiful video with a nice Beth Orton song that talks about how can I make this full screen now? I've lost that. All right, is this OK? Sorry about that. I don't know how to get rid of that bar on the top. I think we were in slideshow mode a second ago. OK, try one more time here. Try this. OK. OK, so that if you were to watch that video, you would see that if we started with the full Hubble deep field or a full COSMOS field, you would take 14 steps to come to a single galaxy when we are coming in factors of 2. So there's a huge amount of dynamic range, and you can see every galaxy with incredible clarity. So this data set gives us a very good place to start. But the most important thing to remember for high redshift studies is everything is changing as you go back in time. For example, galaxies are getting brighter because star formation rate is higher. We're forming stars. We know that the wavelength is changing. The size of the galaxies might be changing. We have to take into account that galaxies may not be the same beasts today and in the distant past. So one of the key things that we had to do was to define a sample as carefully as possible. So we try to create a sample that really compares apples to apples at all redshift ranges. So we use these criteria, assuming that the luminosity function changes by 1 magnitude over to z of 0.9. We stop at a redshift of 0.8 because at that point, the Hubble data goes into the rest frame ultraviolet where bars disappear. We use an SED typing. So this is the kind of work that Olivier here does quite a bit, and it's super useful for us to use these catalogs because it allows us to distinguish, at least initially, between galaxies that are elliptical versus disk galaxies. And then we reject compact objects and obviously merge systems. And then we also only want to use face-on systems because if it's an edge-on system, you can't see a bar. So when you make all these cuts, the sample is complete, but you go from 2 million galaxies to about 2,000 galaxies. So how do you identify bars? Well, it's easy. You would say, how hard is this? Galaxy Zoo does this all the time. Your eye can identify a bar very easily. This is the nearby universe where bars are very, very clear. However, as you go to more distant galaxies, so this is from the Abraham et al. Survey, you can see it becomes much harder. These were all galaxies that were called bar by Bob Abraham's study in the Hubble Deep Field. And you'd be hard-pressed to say that those are bars. It's very hard. If you want to see a bar, you can see a bar because you are a natural classifier. Your brain, due to evolution, is wired to find sheep in the clouds, or find a rabbit. You can find any kind of thing that you want in these clouds. So we want to avoid the bias that comes from naturally your brain identifying bars if you want to see bars. And there's an interesting story I can tell you about de Vaucluse on how he made his students identify bars. But we decided that in addition to using your eyes and your brain, which are very, very powerful, we want to use an independent method. So we use an isophote fitting method where we fit isophotes in galaxies, and we look for this characteristic signature of a bar where the ellipticity increases, drops by about 0.1 at the end of the bar, and the phase angle changes by 10 or 20 degrees so that we can tell that's a bar. It's not perfect. We know in 15% of the galaxies it fails, but we tested this very carefully with the 2-mass galaxies. That was the best data set available at the time in Menendez-Del-Mestre et al. So we used these 2 independent methods for identifying bars. And here was the main result, right? So this result was from the Hubble data from COSMOS. And what we find is that, so on top is visual classification. On bottom is ellipticity and position angle classification. These are all the bars, and these are strong bars. And what you find is in that every step, the bar fraction is decreasing. And so this is contrary to previous results, which said that the bar fraction was constant. We see significant evolution in the fraction of barred spiral galaxies, where the bar fraction is changing by a factor of 3 over the last 7 billion years. More importantly, you're able to see precisely the rate at which it is doing in each billion-year bin. And we're able to put error bars because we do careful statistical analysis of how significant our results are. So this means that the universe was a very different place 7 billion years ago, with only 1/3 of the disks being mature and in place on the Hubble sequence compared to today, because only 20% of disk galaxies had a bar. And this is the most important takeaway. There's a significant decline in the bar fraction over the last 7 billion years. But the strength of the paper is not in this result, because every selection effect will give you this result. So I don't have time to go into the details, but I have like 8 backup slides where I can take you through every step. It took us 2 years to write this paper because we did a very careful analysis of every selection effect. from the size of the galaxies, from band shifting, from artificially redshifting galaxies and putting them in the data and repeating the analysis, using nearby galaxies and looking at what we see in nearby galaxies as a function of wavelength. And I will tell you that this is just a robust result. So I was very happy with this result. And the nice thing is it's actually consistent with all the past surveys. So a little complicated plot, but the red points are the initial surveys from Abraham et al. These black points that you see here and here, those over the 7 billion years, those are the COSMOS data for all bars and strong bars. These two data points are from Jogi et al. They also saw a decline, but they chose to draw a straight line. And then these three data points that you see, if I can find them here, this one, and this one, were from ALMA Green et al., who are also co-authors on my paper. But if you correct for selection effects, they also get a straight line. So, I mean, they also see this decline. So the point is that all of the data are consistent if you evaluate them correctly. The previous work was impacted by their selection effects and small number statistics. And since then, various observational and theoretical studies have validated our results. The best story for me is Frédéric Bourneau sent me an email, and he said, Kartik, you won't believe what we found in his simulations. His student had been simulating galaxies, and they were able to reproduce our data without ever looking at our data, just from the theoretical simulation. So I was very happy that all of this hard work paid off. In addition to that, we're able to divide the galaxies in their galaxy properties. So now I'm looking at function of the galaxy stellar mass and the total bar fraction. And the top line shows you the bar fraction in different mass bins for the low redshift bin from 0.2 to 0.4. This is the intermediate redshift bin, and this is the high redshift bin from 0.4 to 0.6, or 0.6 to 0.8 rather. And what you see is that the majority of the evolution is happening in the low mass systems. This means that bars formed first in the high mass systems. And in the paper, we also look at this as a function of color and the central concentration. And what it means is that the early type disk galaxies matured first. It's another example of downsizing. And it says that the more massive systems formed first and were in place, whereas the low mass systems formed last and came into existence. And I think this is a really cool result, and I'll show you. We've been able to follow this up at low redshifts. And one of the things I really want to do is to connect the low redshift to the high redshift world, which rarely happens. Also, the things that you can't read in the bottom says the sample is complete for all galaxies that are 10 to the 10 and higher based on the mass sample. So, I'm proud of this figure because I think it's as good as we could have done in 2008. Other work has shown that ellipticals formed more than 10 billion years ago. And our conclusions then are that the high mass early type spirals were already in place more than 7 billion years ago. And majority of the evolution in the universe happened in the last 7 billion years in low mass blue spirals. And today, that is still happening. Okay, it's just everything has slowed down in the universe. So things are happening, but they're happening at a very slow rate. OK, so what about bars in the local universe? Normally, I would play you the Cheers song, but for most students in this room, they have no idea what I'm talking about. This was a very famous sitcom, and the song is "You Want to Go Where Everybody Knows Your Name." It's your neighborhood bar. So what's happening in our neighborhood? What are the bars doing? So in order to do that, there are a lot of questions. What is the precise bar fraction? And the reason we want to ask that question is because most studies reproduce the de Vaucler's result. But there are some papers in the literature that say the bar fraction is much lower. Some are reasonable because they use a different definition of a bar. Some are just totally delusional. So I would, and I really dislike that because it adds so much noise when you're trying to make progress, because you now have to take the energy to go through and disprove a poorly chosen sample or a poorly defined bar. And the reason for all of this discrepancy is different definitions of a bar. Very important, sample size and completeness, and how you choose your denominator, and the quality of the data. So what we need is, again, just like COSMOS, what we need for the local universe is a very large foundational database that can allow us to understand the stellar structure in nearby universe. And to do that, Spitzer was a fantastic instrument to do this. So when the warm mission started, there was a call for proposals that could do large surveys. And we put in a proposal called S⁴G, the Spitzer Survey of Stellar Structure in Galaxies. And it is the largest and deepest homogeneous survey of nearby galaxies. And it will remain the largest and deepest survey of nearby galaxies because Spitzer was so sensitive that we chose them with these criteria. We had to go back and do it again because we messed up on the heliocentric velocity criteria, and we missed out on gas-poor galaxies. So we went back and redid those. So we had over 800 hours of Spitzer time. We got over 3,000 galaxies, between these two studies. We mosaicked them out to 50% of their D25 diameter. And only with 4 minutes per pixel, we get an incredible depth in these images, right? We go down to 27 magnitudes per square arc second for the isophotal magnitude that we're sensitive to, which means that we can trace the stellar surface density in these galaxies to much less than 1 solar mass per square parsec. So if you want to do work in the nearby galaxies and understand the stellar structure, this is the survey you want to use. All of the data is public, including all of the enhanced analysis that we did. So for students or anybody interested in nearby galaxy, I encourage you to use this data set. I also want to say I'm really proud of the policy we set up in the team very early to make sure that we were making all the data public, that nobody was allowed to carve out their own areas of science and prevent others from doing science. In fact, when there were two teams on our team, or two groups on our team who wanted to do the same science, we encouraged that. We're like, you can work together, but you can also work in competition, but sharing information, because if two papers can validate the same result or the same question, coming at it from different angles, both of those papers can be very valuable, and they can both help each other. We also had some very, I think, important rules for authorship, where we made sure that for these large teams, not everybody was on every paper. Cosmos has a very similar policy. I don't think we may have written it down, but anyway, this took a while to do. But if anybody's interested, I'm happy to share this policy. And the questions we wanted to ask when it comes to barred galaxies is to ask all these questions. And you can see bars are so easily identifiable in this S⁴G data. One of the things you might notice is that even though these are 3.6 micron images, right, in the L band, you see a lot of little stars and background galaxies. And that's because the 3.6 micron data from Spitzer actually is very similar to a deep blue band data, B band data, because the 3.3 micron PA emission lights up every time a stellar photon hits it. So the beauty of the 3.6 and the 4.5 micron data is not only do you have a beautiful infrared data set, but you also have an idea of where the stars are. And we didn't expect that. So I thought that was pretty cool. Subtracting the two gives you also where the dense dust is, which we haven't done. So what do we find as a function of the mass of galaxies? Now this is for the S⁴G data. And again, we do weak bars and strong bars. And what we find is this dramatic decline in the bar fraction at roughly the mass of Magellanic systems. So now at 10 to the 9.2, we are seeing that bars are disappearing. Remember that this is consistent then with the COSMOS data. At 10 to the 11.2, half of the galaxies were barred at Z of 0.7. At Z of 0.5, we came down in the mass range to 10.5, 10.6. At Z of 0.2, 0.3, the local universe with 10 to the 10 solar mass galaxies, half the galaxies at bars. And then today, at Z of 0, that number, the epoch of evolution, is at 10 to the 9.2, which means today, galaxies that are forming bars, that are becoming massive, cold, dynamically supported, are Magellanic-type galaxies. So if you want to understand how does dark matter and baryonic matter separate from each other, how do galaxies form, that's where we want to look, are the Magellanic systems. So those of you studying low-mass galaxies should sell yourselves as galaxy evolution pioneers in the local universe. The other interesting thing is that the bar fraction is what de Vaucluse said in the 60s, but the bar fraction is very low in the low mass systems, and that's contrary to some other studies, and we can talk about that later if you want. So the summary so far is that the total bar fraction has declined by a factor of 3 over the last 7 billion years, but we could only go to redshift of 0.8 because that's what HST could do with NICMOS. And we need something like JWST to push further. And so that's what I hope to do when I'm here. We also were able to see lots of things in terms of low mass systems, in terms of how downsizing happened. And we want to try to see how this happens at higher redshifts. There are papers that I didn't talk about that are listed up there. We also showed that hot disks cannot form bars. So I know there's a lot of people here who do stellar spectroscopy, and it would be very interesting to follow up many of these systems to understand where they form on the Tully-Fisher relationship as a function of redshift. So we can try to understand how galaxies go from having all these little things, clumps fall onto it, which heat up the disk, to become cool disks to then allow the bars to form. And so in that paper, Hot Disks and Delayed Bar Formation, we talk about that. Again, I don't have time to talk about that, but it's something that would be really fun to do given the strengths here at the LAM. And then how does this change with dark matter and gas? So there's a paper that we did, sorry about that, got messed up, where we really try to use the 1 millimeter continuum as a proxy for molecular gas as a function of redshift. In a paper with Nick Scoville, who was my postdoc advisor, but we did this only a few years ago. We're able to use telescopes like ALMA to quickly look at how the gas varies using continuum data. And it would be very interesting to do this as a function of time in redshift to see what the role of gas is. And this is a paper by Elia again that shows that if you just have a purely gaseous system, a bar forms very quickly, and then it gets destroyed and nothing happens. But if you have if you have less and less gas, then you can see that the bar formation time frame is delayed. And in fact, for galaxies that are 75% gas or 20% gas, the bar formation timescale is different. So how do we check that? And that would be interesting. The thing that got cut off in the middle is the only way to understand the dark matter distribution is using strong lensing. And so I don't know if Euclid data would be good enough, Euclid plus Roman. But in individual galaxies, it would be interesting to see the dark matter profile and see whether they have bars or not as a function of redshift to see how that changes. All right, so this is my first half of my talk. I hope I'm not way over. OK, I'm going to go a little faster, sorry. Other research that I don't have time to talk about, but in my audition for the Safe Space for Science I discussed, is the work that I've done in millimeter astronomy using ALMA, where we have incredibly good data on nearby galaxies. Of course, you're familiar with the FANG survey, but very early on, we also collected beautiful data on this galaxy, NGC 1097. And I think we can write like 5 theses just on this galaxy. This is the CO data. We have such good, this is the M51 of the south. The beauty of a bar galaxy is that because it has many dynamically distinct environments, we can try to understand how the gas and the gas dynamics are impacting star formation. And one can do that at the bar ends, in the ring around the bars, and outside in the normal disk to understand that. So we have done some preliminary work here to show that in the bar dust lanes, which is in here, there's a lot of gas, but there's almost no stars. And we need to quantitatively understand what is the dynamic signature that prevents bars from forming in molecular clouds. And we have the data now from the ALMA data that we can do this. And there's a huge amount of data. I was part of the SINGS project as well. This is the nuclear ring in 1097, and you can see just a ton of lines. And there's so much science we can do here in terms of looking at different molecular lines and different atomic lines to understand the electron density and the gas density. So just a ton of work that we could do. So I'm really excited to come back and do science because, as Stefan implied, for the last 10 years, I have been at NASA and the White House and other places, not actively doing science, but trying to keep a toe in it. So I'm excited to come back and do that. But I also wanted to introduce you to kind of my scientific journey. So as you could probably guess, I was born in India. Map of India you won't see very often because Jammu and Kashmir look very different. I grew up in Mumbai. And this is my family when I was, I think, 8 years old. I was always the shortest kid in the class, so I'm probably standing on something there to be taller than my mom. First time I ever saw snow, we went to Kashmir in 1980. And when we were young, we really didn't have much, right? So, but it was a very happy childhood. For me, renting a bike was what I really enjoyed doing. Family and friends was everything. And America was a dream. I always imagined what it would be like. I got really excited about astronomy because my uncle and aunt gave me a Voyager picture book. And I got to learn all about all the stars and all the planets in the solar system and the satellites. The other thing that happened was school field trips to Nehru Planetarium, which were amazing. So in Mumbai, you could still see stars in the 1970s and 80s. But the planetarium would just always get me. I just really loved thinking about what is out there in the cosmos. And then the very important thing happened in the 1980s is we used to only have one black and white channel called Doordarshan in India with one children's program on Mondays at 6:30. But then we had American television and color television come to India when India hosted the Asia Games. So none of you probably know this, but does anybody know what this sitcom is? Oh, you do? Oh, yeah, Galen does. It's different strokes. It's crazy. It's interesting. But the other show, this was one of the first shows, the other show that came was Star Trek. We didn't have a television in our house. Like I said, we didn't have a phone, we didn't have a car, we didn't have anything, actually. So I would run around the building on Sunday mornings to ask somebody to let me watch TV. And Star Trek just really got me, and I really wanted to become an astronomer. My parents took a brave step. 1986, we left Mumbai. My dad was 47, and my mom was 44. And they came to America for the family, for my sister and I, because we were both interested in science. And as I said, we were a very close-knit family, but because of the conditions at the time, we were immediately split apart. I ended up living in Iowa with my uncle and aunt. My sister went back to India. My dad moved to New York. And it was 11 years before we were all together again. So it was a really transformational time for my family. I can never thank my parents enough for taking this brave step. My scientific journey has been all over the place. I went to Grinnell College for my bachelor's in physics, a liberal arts college. And I was very happy, even though it was in the middle of Iowa and you couldn't leave, because I knew I wasn't going to be moving. And then I ended up going to University of Minnesota in physics, but almost dropped out. It was a really toxic environment. And I almost quit science completely. I ended up getting a master's in physics education. I ended up doing a master's and PhD at University of Maryland. I was at Caltech. My family still needed money, so my goal was to get a full-time job, and I became permanent staff very quickly after that, working on Spitzer. I think Ghislaine and I overlapped at Caltech during this time, and maybe Marie as well, from 2001 to 2009. At that point, my mom said, we're not moving to California. If you want to be closer to us, you should move back to the East Coast. So I moved back to NRAO and ALMA, and then eventually NASA, and then the White House, and then back to NASA. So I'll just give you a quick tour of kind of what we did. These are all my alma maters. Oh, that didn't come out very well, but that's the beautiful Grinnell College campus in Iowa. My life was really, I first started working as a radio astronomer. In fact, I worked on every millimeter interferometry and helped build it except for the submillimeter array. So BIMA, I built expanded it to the 9-element interferometer. I was telling Stefan yesterday, I spent entire 2 weeks fiber splicing cables inside the little cabins of the BIMA array as we expanded the telescope. And then I worked at OVRO, then Karma, and then ultimately ALMA. And then I moved on to really working with space telescopes as the Spitzer instrument scientist. For 9 years, I had a Big Bang Theory life. I was the Indian astronomer, like Raj, a complete nerd. But I loved it. My time at Caltech was one of the best academic times. Then I went to, and what I talked about in terms of science was all of the things that I showed you before. I moved to NRAO, and really spent 2.5 years living in Chile as we built ALMA. I was there the night we got phase closure on the antennas. We celebrated with water bottles. And probably one of the best things that I was able to do was help get ALMA going. So I was the commissioning and science verification liaison for ALMA. I had a group. I was on tenure track. I got my tenure. But the thing I'm also very proud of are these two programs that I established when I was at NRAO, the National Astronomy Consortium. It's a partnership with 17 historically black colleges and universities, and 7 predominantly white universities and 3 centers, which fundamentally changed the demographics of astronomers in the US, and a program that we started and did in South Africa from 2010 to 2016. And the reason I worked in South Africa is I was offered an endowed research chair in South Africa. I didn't take it, but I was really keen to change kind of how astronomy was done across the continent. This was my life in Charlottesville. You know, I volunteered, had the incredible pleasure of meeting President Obama, was able to build my own house, and I thought I would live there for the rest of my tenured, cushy career, but I really hated Charlottesville. And so you guys are all familiar with the right to, you know, the right-wing march that killed Heather Heyer, and I was just unhappy. In 2013, I was invited to sit on a committee that laid out a vision for NASA astrophysics for the next 30 to 50 years. Especially for the students and postdocs, I encourage you to read this document, Enduring Quest-Daring Visions, which lays out a vision of NASA astrophysics for the next 3 decades. And it really got me excited about wanting to go back into doing science management. When I come to Charlottesville, I was offered a AAAS fellowship, but I hadn't taken it. So I go to NASA. So this is kind of the NASA org chart, and this is where I was for the first sort of 5 years or so, 5.5 years, in the Science Mission Directorate. So what I did at the Science Mission Directorate, so in terms of the missions that I oversaw, as you were asking, these were the missions I was in charge of. So it was everything longwards of 1 micron, except for New Athena, which I started working on right before I left last. So Sophia, one of the hardest missions to manage. Everything I learned about management was from that. Really happy to do JWST as the deputy program scientist. Spitzer was my favorite mission because I started working on Spitzer as a postdoc, and then I was managing the whole mission. And then we just launched SphereX, which I'm super excited about. And I'm excited about New Athena. Origins is a mission that we have a concept for. I also was in charge of the Hubble Fellowship. So some of you may hate me, but I think it was the right thing to do is we merged the 3 fellowships, Hubble, Chandra, and Sagan, into 1. So there's only 1 application process. This was a very difficult thing to do, actually. We can talk about that more. For a year, I did a lot of public affairs and communication. Never want to do that again. I managed a big portfolio of technology, longwards of 1 micron. I'm a big fan of ballooning as a great way to do far-infrared astrophysics. We did Lab Astro, and a lot of funding of technologies for the infrared. And a lot of strategy. So because at headquarters, we do a lot of strategic thinking and putting policy in place. I got bored with astrophysics, so I then ended up working in earth science for a 1.5 years in applied sciences, and primarily worked on a number of United Nations Sustainable Development Goals, especially 14 and 15 and 11. And then the thing I'm most proud of there is I managed a group of economists for a project we call Valuables, where we built a macroeconomics framework for the valuation of societal benefits from Earth observations. So those impact studies are on the web, and they're super helpful and coming in really handy now as Space 2.0 gets going. I also did a lot of work on inclusion. I was the chair of the Asian American Pacific Islander group, and also the co-chair with Thomas Zurbuchen for the Anti-Racism Action Group. And we did a lot of work on NASA's core value of inclusion, which was adopted in the first Trump administration after the murder of George Floyd. So I'm really proud of that work, and I'll talk about that a little bit. I really kind of wanted to leave the US, and my wife's like, no, you have to do more for the country. You know, it's given you so much. So I kind of raised my hand and was able to work at the White House after that. My first time at the White House was working in this building, which is the old executive office building. It's the most beautiful building in DC, in my opinion. This is the main residence. This is the West Wing. The Oval Office is right here. You just cross, you just walk down some stairs and go over here. And that second building is the new executive office building, which was my second tour of duty at the White House. So as I said, this is a beautiful building. Highly recommend going to visit if you get a chance. If you come to DC, I'm happy to take you there. I still have enough connections in the White House to be able to do that. So my first tour of duty at the White House, I was the AD for research infrastructures and science equity, which meant overseeing the infrastructure for science across the nation and internationally. And I got to do some really cool things. I was the chair of the Advanced Manufacturing Subcommittee, and we set out the quadrennial strategy that's required by Congress on how we're going to do advanced manufacturing across the country. Every day at the White House was like going to graduate school for the first time. Somebody would come, they would give you a new problem. You didn't know anything about it. By the afternoon, you had to become the expert. By evening, you were writing policy. So it was a very, very fast-paced life, completely exhausting. When you're at the OSTP, you don't actually, even though you have the business card of the White House, you don't have budget power. So our power was using that White House card to convene, collaborate, convince, and cajole the US government through executive orders, working with OMB for money, and policy documents to move the priorities of the administration. Some of the cool things I started working on were in energy space. On space solar power, I helped organize the first fusion summit at the White House, and we did a really wonderful report on net zero game changers technologies. There are 37 technologies in there. So this was a lot of fun, but this was my third toxic environment, and I left the White House. Very proud of the work that we did. So these are all publicly available. Lots of work that we did on the policy side here. And just some pictures to show you, people would say, do you see the president? I'm like, yeah, he's my office mate, because it was COVID, and we were on the 4th floor, and Joe Biden would go by regularly because the video room was on the 4th floor. So I would step out of my office, and if I saw people with machine guns inside the building, then the president or the vice president were there. So that's with Jill Biden. You can see this is, one of the perks is you can take your family to the White House as much as you want. Vice President Harris, this is for Diwali celebration. We would always take a group photo. If you've seen the HBO show Veep, you can see that the inside looks like that, where in that building, the vice president, the OMB director, everybody is in that building that I worked in. The difference is in Veep, there are windows on the outside. That's not the way the building is set up. So small errors. And the second floor of the building is just beautiful. So I loved working there. You got lots of perks. You got to go to state receptions. This was a typical scene at the White House on most days. This is during the Biden administration. And you can see all of these Suburbans idling their cars the entire day. just polluting the atmosphere. And there was only one electric charging station. Anyway, it's just kind of funny that it was very ironic that that's the way it was, So we also got to go, to the Kennedy Center to see a performance. And there's a bowling alley at the bottom of the White House. So I had one of my birthday parties there. It's a lot of fun. I ended up coming back to NASA. I was super bored. So I did a lot of work with the National Space Council. And then somebody called me up and said, hey, do you want to come back to the White House? So I went back, but this time not on the policy side, on the budget side. So I served as the program examiner for Department of Energy Office of Science. So this is the entirety of the portfolio I had to manage, and an $8.5 billion budget. And so worked on everything from advanced scientific computing research to biological and environmental sciences, down to nuclear physics and accelerator R&D. And this was the best job I ever had. I would say I would go back in a heartbeat because the people working at the Office of Management and Budget are just true hardworking civil servants who you never hear about, but they do so much work to make sure that the business of the nation continues from one administration to the next. The nice thing was the COVID was over, second time at the White House, so those are my in-laws. This is the press room that you see on TV, outside and all. It's very small, actually. That's my niece, and my wife pretending to ask questions. And again, here I really worked on Department of Energy, and I could tell you lots of great stories, but all I'll tell you is this was a fantastic job, but very hard, because you're dealing with 3 different budgets at any given time and managing an entire department. Some of the things that I'm really proud of is I was able to write the chapter in the 25 budget for Department of Energy, was able to take my parents to the White House and see the West Wing, et cetera. So I like showing this picture because that's us in Kashmir, and then us, 30 years later, super happy with my service to the nation. I decided to come back to the White House. I was then in the Office of the Chief Scientist as the Associate Chief Scientist, reporting directly in the administration. Our office reported directly to the administrator. And in that office, my purview was to look at all of science across NASA. So not just science in the Science Mission Directorate, but science in aeronautics, Space Technology Mission Directorate, looking at science integrity. And I was really proud of passing the NASA Public Access Policy. But the other nice thing was also I could start doing science again. So I was very happy to come to COSMOS meetings in Japan. This year I came to the one in May to Marseille. But of course, in March of last year, unexpectedly, we got fired. So for the first time in 4 decades, I found myself without a job. And Olivier, I'd send a Slack message on Cosmos saying, hey, just so you all know, I don't have a job. And Olivier said, oh, you should apply for the Safe Space for Science program. And so we've been working on it since March of last year. It's a long process. It's been an amazing experience. I cannot thank the French people and the French government enough for creating these programs. I've been in a lot of French media, so we had a producer from Envoyé Spécial come out and interview me. I was able to meet with Minister Baptiste and Macron. We're still working on this, so we'll see how this goes. Beyond research, what I hope to bring here is the experience I have with ALMA and SKA. Now that France is a member of SKA, it would be nice to see how we can better work with this new telescope, and especially with NGVLA coming on. Of course, I've worked with a lot of NASA space missions, and with all the CNES work that goes on here, with Prima, Roman, Rubin, and Euclid, I'm really hopeful that we can work on those things here together. I'm working on a new project, moving the Sunia Abzeldovich array to Morocco. And we just had our first meeting a week and a half ago. And in talking to people here, I understand that Aix-Marseille University is interested in being part of a consortium of Mediterranean universities. And because the language that a lot of people in Morocco speak is French, I think this will be very good synergy where we can expand the efforts of what we're doing to build a new radio astronomy community in Northern Africa in millimeter and submillimeter waves. And of course, LAM had the nanosat program, so hopefully we can see what we can do about doing capacity building. I talked about this idea at some point. I think it's very difficult for people to move to France, especially later in life, right? Like it's just, I'm amazed at what my parents did in their 40s, but now in my 50s, it's not easy to try to think of completely leaving the country. So what I've encouraged, President Macron, I said this to Minister Baptiste as well, is to say we should have a lot more flexibility. What we should really do in this time of chaos is double down on creating strong global partnerships. So today, the US has a lot of concerns about scientific funding, maybe a lot less scientific funding. So maybe France and Europe can help with doing partial and joint appointments over multiple years so that we can work on shared research, shared values, shared excellence, and shared personnel. And then we should really set up with private and philanthropic funds something like a Center for Science Refugees. It's not the name that we want to use, but the idea would be that when people come here from US institutions or elsewhere, they really try to talk to the entire Marseille region on why these kinds of global cooperations are important. Of course, there are many other programs like that already set up, so we can learn from them and try to set up such a center here. I didn't talk about this at all, except slightly mentioning it, but for 30 years, because I almost got removed from science, I've been working on creating inclusive environments wherever I go. After 30 years of working on a variety of things, I can boil down everything I know into these two mantras. You can't be what you can't see, and you don't know what you don't know. And I use that in terms of trying to figure out ways in which we can create more inclusive environments. And for the last few years, I've been using a design thinking process to hold workshops. Some of you might be part of CMBS4 or the TIM program at University of Illinois, and I've done a few workshops there where we try to talk about how can we implement more inclusive practices. One of the things that we have done is we pioneered inclusion plans at NASA with Evans Quinnipiaco, and now that's been adopted across the US government, so Department of Energy has them as well. So I hope if anybody's interested in this, happy to talk about this more. But the one main message I'd like you to take away, besides those two mantras, is our job is not to focus on diversity. Because focusing on diversity, I can count how many women are in the room or how many people of color are in the room. It should be important that we focus on inclusion and creating inclusive practices. And if we can focus on that, I think a lot of the other things become simpler for us to do. So thank you again for the opportunity. It's an incredible time. There's a ton of great archival and new data, amazing amounts of science and work we can do together. So I don't expect, because my position is temporary, I'm really trying to talk to everybody here to say, how can we work together? Because I'm not interested in setting up a big empire, big group here. You know, I really want to try to work with people to create things that are going to be long-lasting beyond my time here, you know, and establish sustainable partnerships that we can carry forward into the future. So I kind of described to you my journey through this. As we said, it's a long process since we started the process for Safe Space for Science. And the Choose France for Science thing has not been announced yet formally. So I've been doing a lot of things since then. So I wanted to leave you with this last slide that talks about what I'm working on now. So if you have a few minutes, do go to this website, empoweredearthalliance.org. This is the nonprofit that I set up in 2020. Part of that, we are using that to move the telescope to Morocco, but a program to create the next generation of leaders who stay in their own countries, in developing countries. And we're doing a project in Botswana to do slum reduction. Happy to chat more about that. I've started to do a lot more work in the private sector. I'm a strategic advisor for Max Space, and we're launching the expandable habitats, 350 cubic meters that fit on a standard Falcon rocket. I'm the chair for the Global Council for the Singapore Space and Technology Association, where we're trying to mainstream and commercialize space in Southeast Asia. This company, Close Carbon, is trying to build renewable methane. And then I'm consulting with the John Templeton Foundation on initiatives on how to do philanthropy better. Teaching at Georgetown this spring just to get my feet back wet. And then here are several boards that I serve on as a volunteer. The most interesting of which might be, for you, might be the Lunar Development Cooperative, where we're trying to set up an economic free zone on the moon in a public-private partnership. For those of you who are not aware, the International Astronomical Union has an Office of Astronomy for Development, which is partnering with us on the project in Morocco, but also on how we can use astronomy to improve the lives of people in society. So I'm excited about that. All right, I'm going to stop there. I know I probably went way over on my time. So questions, let me know, and happy to take. Yeah. So please come talk to me if you have any interest in any of these things. But happy to take questions as well. I know we're over our time.
Thank you, Kartik. So if you have any questions?
I've stunned you into silence. Yeah, go ahead.
So I have a question about the astrophysics.
Sure. Go for it.
Thank you so much for the talk, though. It was really nice to see all of your life and the places that you've been. It's incredible. So about the astrophysics,
Yeah.
I was interested in when you started talking about when you introduced the galaxy shapes and as a function of their evolution.
Yeah.
basically to say or like probe whether a galaxy is going to be is going to have a bar or is going to have a certain shape instead of
Yeah, so I think that that's a really good question. There are, from simulations, we know we can measure the quadrupole moment if there is an m equals 2 mode. So what are the conditions for us? It would have to be using the gas kinematics and an understanding of the mass of the galaxy to see if an m equals 2 mode would be set up. That's kind of one theoretical way of approaching it. What we did with the Deep 2 data is measure the velocity dispersion and the rotational velocity in the Tully-Fisher measurement, and that can give you an indicator. But it's a very difficult thing to say, is this galaxy going to form a bar? Because we can only measure either before, when it doesn't have a bar, or after. We can compare those two, but you're never going to catch it and go, yes, this is definitely going to happen. So I think if you measure a dark matter profile, for example, and you see that the dark matter is dominant, but it may still form a bar later. We only see the before and after snapshots. So your question is very interesting, but very difficult to actually do observationally. There's no set of criteria for before a galaxy is going to form. I can tell you what the criteria are in a galaxy once the bar has formed. We know that it's going to be dynamically cold and rotationally supported. It will be on the Tully-Fisher relationship. So yeah. Yeah, go ahead.
Following on this, do you need resolved spectroscopy to identify a bar in the spectrum, or can you do that in
No, you can identify a bar just morphologically because it's a pretty clear signature in the infrared. However, the kinematics are really important because it gives you it can allow you to measure what the torque might be at a given point, and then therefore allow you to understand how the stars and the gas are going to act in that system. So we've really struggled with this. There's a 1997 paper, Reagan, Sheth, Vogel, Toybin, where we looked at the velocities of gas in barred galaxies to do the kinematics. And it's so hard to interpret because you don't know what the near side and the far side are. So I went to the AAS and I actually printed out a galaxy and a model, and I put little arrows on it to try to explain to people what we were seeing. I think it's the next frontier. If we could have a very detailed understanding of the kinematics of the disk in stars and gas to better understand the impact of a bar on those two key baryonic components in the matter. Initially, when people were studying bars, they thought bars are going to be extremely important for secular evolution of galaxies. But almost every study we have seen says they don't do much. They rearrange the gas. They bring the gas to the center, but they don't seem to be feeding the black holes in the center. The chemical gradient across the bar doesn't seem to be as shallow as people had initially predicted. So this is work with Patricia Sanchez-Blasquez in Madrid and others. So people are looking at that. Yeah, so I think I can find interesting things to do, but I'm not exactly sure what the application would be. Yeah.
So I wonder if you could briefly place galaxies in the picture you described. So I know it's relevant, but I'm not exactly sure where its strengths were with respect to what you showed.
Yeah. So I mean, I think there's a paper by Masters et al. That talks about what Galaxy Zoo does is it goes to people and says, does this galaxy have a bar or not? What is the shape, et cetera, right? So people enter the data. But what Karen's paper shows is that depending on the confidence interval you use, which she calls the p-value, you can reproduce any result as a function of redshift. So I don't think Galaxy Zoo is very useful for doing science in this regards. It's useful to engage people to understand what galaxy shapes might be, what structures might be. But I don't think you can really use it to do good science because of this problem. Yeah, and the story is de Vauclair's used to give an exercise at Texas to his class. He'd give a lot of pictures to people and say, identify the bars. And if they didn't find as many bars as he had said, he's like, you're not looking hard enough. And so that's the definition of a bias. And a lot of papers, like in the Nair and Baratza papers, for example, they claim there are lots of bars in low-mass galaxies. But they do it simply by eye. Like Preeti says, she does 2,000 galaxies a night. And Deborah and I, when we do it, we can't do more than a few hundred because you're trying to fight your biases to keep identifying bars. So I think you have to be very careful with visual classification of galaxies. I think your brain's powerful, but you have to be really aware of the biases you might have. One of the things I didn't mention is the thing I'd really like to do now is to see if there are any artificial intelligence methods and using priors to be able to identify bars automatically as a third way for us to really understand bar fractions, especially with the JWST data. That would be really great. And then we can be really sure if there's a bar or not. Going back to the kinematics question, the kinematics can definitively tell you whether there's a bar or not, right? So I think, but because it takes so long to do one galaxy, it might be places, we might have to do a smaller sample than 2,000 or 3,000 galaxies. Maybe we take 10 barred galaxies, 10 galaxies where we're not sure, 10 galaxies where we're sure, and try to understand, try to do it as a calibration for these other methods of identifying the fraction of bars quickly. But that's just my opinion. But if I'm wrong, I'm happy to be wrong. If you think we can do 2,000. I'm talking about full 2D resolved kinematics of a galaxy at a sub-kiloparsec scale. So something like the Megara instrument on the GCT, where just talking to Armando Gil Paz, it takes a long time to do each galaxy because either you do spectra, fiber-fed spectra, and then the field of view and the throughput, means you can maybe do 2 or 3 galaxies a night. So it just takes too long to do thousands, So if the technology has changed, I'd be happy. Like, if you go to multi-object spectrographs and, you can do a single slit. But if you want to do a 2D field, which you need to identify this, then it would take longer.
That was my original question.
Sorry, misunderstood you. So, yeah. Other questions? I know I'm sorry to keep you guys longer. It's a lot of slides.
Any other questions? In any case, so Kartik, you will leave on
Wednesday.
Thursday?
Yeah,
On
Wednesday.
Wednesday?
Yeah, Wednesday. Yeah.
So he's still here after Wednesday, so feel free to come and talk with him. He will be at the E114 or 13 office.
Next to Patrice's office and near Olivier and others. So yeah, I'd love, or if you want to set up a time when we can meet, then let me know. Today is a little complicated with a lot of meetings, but yeah. Monday, Tuesday are really wide open, so it'd be really good to chat with as many people as possible. The 2 grants provide a lot of funding, but I really want to work with folks here to pair up and co-supervise students and postdocs to the extent that we can, because I'm going to be going back and forth a lot to the US because my parents, my in-laws are in their 80s, they're in the US. So. And my wife's job is in the US, so we're not, we cannot just move and settle here because of family constraints. So I'll be going back and forth. So it'd be very nice to partner with people here to be able to work with students and postdocs.
Okay, so thank you.